All right, guys, here we are. So we are about to talk about some non-constant sum mixed Nash problems, and we're gonna kind of take them in order here. So, as you know, non-constant sum just means that the totals in each of the squares don't add up to the same thing. Now you notice here, this is kind of non-constant sum-ish, like right? It's got a little bit of that. It's got 6, 4, 4, 5, 2, 6, 7, 0. Like this feels a little competitive, right? You know, I mean, like when row does well, 7 or 6, column does less well. When column does well, 6, 5, row does less well. So this is sort of like a one that like I hope will make some more sense as a non-constant sum problem, and then we'll get to some ones that make less sort of like sense in sort of a conceptual way. Okay, but the good news is that mathematically these are the exact same problems as the problems that are constant sum. So to do that, if I want to find rows mix, right? I want to say that P is percent south and 1 minus P is percent north, right? Okay. So the payoff for east then, right? If I'm east, the payoff for east for column going east, right? That would be if they go east, they get 6 times the percent chance it's south. So 6p plus 0 times 1 minus p. And for column going west, right, it's going to be 4 times p plus 5 times 1 minus p. We set those two equal to each other. This comes out to be just 6p, which is nice. And this one comes out to be 5 minus p. So we set these two equal to each other. 6p equals 5 minus p. 7p equals 5. P equals 5 sevenths. Okay, and that gives us a payoff for column is just plugging this back into either 6p or 5 minus p. And it comes out to be that's 4.28. Okay, that might be 4.29. I don't remember what the rounding is, so apologies if that's wrong. Okay, so what this means, P is 5/7, right? That means that the row player will play south 5/7 of the time. Why does that make sense? So I'm looking at these numbers, I'm saying why does that, because south is 2 and 6 and north is 7 and 4. Except, what's column likely to do? Column is likely to hang out in west a lot. 4, 5, right? And if 4, 5 is better than 6, 0, so if we think column's going to go west a lot, then row should go south more, right? Okay. That makes sense to me. All right, then for columns mixed, okay, for columns mixed, right, we've got Q equals percent east and 1 minus Q equals percent west. Okay. So then we need rows payoff. So rows payoff for going south, that's going to be equal to 2Q plus 1 minus Q. Oh, well, sorry, that's just, I forgot the first part of this, plus 6 times 1 minus Q, which if you do the math outright is 6 minus 4Q. And columns payoff, or no, sorry, not columns, rows payoff still for north is equal to 7Q plus 4 times 1 minus Q, which is 4 plus 3Q. We set those equal, so 6 minus 4Q equals 4 plus 3Q. And this is 2 equals 7Q, so Q equals 2/7. That means that column is playing east 2/7 of the time and west 5/7. So that actually makes sense. So column's going to play west 5/7, and row is then going to play south 5/7. So they're going to end up here the most. That kind of makes sense, right? 6, 4, right? That's not as like that's close to the best for row, and it's like not the best for column, but it's actually like not terrible, right? 4, their best is 6. And their expected payoff is 4.86. So their expected payoff is actually better, even though they're the one with the 0. The expected payoff for column is better because column basically is guaranteed to stay in, like, or very likely to stay in these 3 spots, and row, and those are the 3 best for column, and we're never going to hit the 7. 7-0 is going to be pretty rare. Okay. All right, so let's go to a game that is just a more generic game here. This is chicken. Now remember, chicken has Nash equilibria and pure strategies. All right, I can do best response here. If row goes straight, column wants to swerve. And if row swerves, column wants to go straight because 1 is better than 0. And if I do the same thing, right, I get this and this. So there is a pure strategy here. But there's 2 Nash equilibria, like one of them is good for one player, one of them is good for the other player. So seems a little dicey, right? So what if we actually wanted to solve for what if there's a mixed Nash? Maybe each player wants to go straight some of the time and swerve some of the time. Okay. So let's go that P is percent straight, and 1 minus P is percent swerve. Now notice I only have to do this once because it's symmetric. So so then I go for the payoffs. I don't have to say rows payoffs, but rows payoff, this is rows payoffs, this is for column. So then rows payoff for straight is going to be -2 times P plus 1 times 1 minus P, and rows payoff for swerving is -1 times P plus 0 times 1 minus P. So we have this is equal to, this comes out to be 1 minus 3P. So we have 1 minus 3P equals -1P, 1 equals 2P, P equals 1/2. And if you plug that back into this right here, or into this one, I guess right here, you get the expected payoff is -1/2 for each player, for both, because it's symmetric. So the question is like a -1/2 is the third Nash? Like the third Nash is, right, if I were describing it, it would be, you know, the mixture is 50-50, right? And the payoffs are -1/2, -1/2. Now that's actually, like, overall that's a worse payoff than this and this. But I mean, it sort of seems like maybe it's more fair, more even. Would we end up here or one of these? Like, I mean, one of these players probably is going to try and force a way. Like, if you're getting -1, you might be like, well, this is better. I'm going to try and force my way there. So it might end up that way. All right, let's look at another version of chicken where I've made the payoff for going straight much, much worse. Now it's -10, -10. Okay, so we're going to do the same thing, right? So P is percent straight, 1 minus P equals percent swerve. Okay, so then the payoff for going for the first, so this is for column again. Columns mix, and rows payoff. So rows straight payoff equals -10 times P plus 1 times 1 plus, or 1 minus P. Okay. And for swerve payoff, it's going to be -1P plus 0 times 1 minus P. So we set those two equal to each other again. I've got -10P plus 1 minus P is equal to -1P. This is 1 equals 10. This is going to be 1 equals 10P. No, not 10P. Yes, 10P. What am I doing? 10P. So P is 1/10. Okay, so this is way down, and that's smart. I mean, like, P is going to play, row is going to play straight, and row and column are both going to play straight way less, right? Because that outcome is so bad, right? That makes logical sense. But here's what's interesting. The payoffs, the expected payoffs are, if I plug in 1/10 for that, it's -1/10. So by making this straight payoff much worse, we end up at 0, 0 a lot more, which means our payoff is just -1/10. Okay, so we actually made, by making the payoff for crashing much worse, from -2 to -10, we actually make the payoffs go, for this third Nash, the mixed one, to go -1/2 to -1/10, which is sort of an interesting outcome, right? It doesn't make sense. But you can still sort of see how this mixed Nash equilibria would end up happening, right? Why not go to it? It's like, especially if it's -1/10, like, right? Would you rather have -1/10 or be fighting over whether you get -1 or 1? I don't know, and could be either way. So that's what ends up. All right, so let's go one more classic game. This is assurance. Now, assurance, you're like, whoa, Aiden, why does this have a mixed Nash equilibrium? Isn't the Nash like here, and this is pretty clearly the focal point, right? Like, that's the best they can do. Why would you have a mixed? It's an excellent question. We're still gonna have a mixed Nash equilibria. It's just gonna be dumb. Like, no one should go to the mixed equilibria. Okay, but by technical definition, the mixed Nash equilibria is true. It exists. Okay, so again, let's say that columns mix is a P equals %A, 8%, and 1 minus P equals B%. Okay, so rows payoff, rows A payoff is equal to 2 times P plus 0 times 1 minus P. And the B payoff, 0 times P plus 1 times 1 minus P. So that means 2P is equal to 1 minus P. P is equal to 1/3. Okay. And we can say that's true for both people, right? So like the P mix is, the P is 1/3 and Q is also 1/3, right? Because again, we have the symmetry between the two sides, so we can make sense. So what's the expected payoff then? Expected payoff, we can plug that right back in, is 2/3. Notice that expected payoff is worse than either the Nash equilibria. This is what we would call like an unstable mixed Nash, right? You're not gonna like find, if you're at this, you could just both be like, look at each other and be like, no, seriously, can we do better than this? Right? You would definitely want to do better than 2/3 because you can both do better. But it is still a mixed Nash by all definitions. Okay? All right. That is it.